Welcome back. Noise in an image can originate from the acquisition, processing, transmission, and storage steps. Removing noise from an image is a desirable objective encountered almost everywhere images are used. Without using an explicit model for the noise, other than it is additive and broadband, we can use linear and also often spatially invariant filters to remove it. Noise removal is an important topic which can be cast either as an enhancement problem, as we will do in this segment, or as a recovery problem, as we will do in weeks 6 and 7. Treating it as an enhancement problem, we are not providing neither a model for the noise nor an explicit metric of optimality based on which a filter is derived. So, in this segment, we'll make use of the material we covered in weeks 2 and 3 and describe and analyze linear and spatially invariant filters suitable for removing noise in images. We'll also show a number of experimental results demonstrating the efficiency of such filters. We will also discuss an example of a spatially varying noise smoothing filter. So with that, let us proceed with this very important and useful material. We will move next to spatial filtering approaches towards enhancement, starting with the use of both linear and nonlinear filters for noise smoothing. Under the heading of smoothing spatial filters, we consider techniques for enhancing an image by reducing the noise that might be present. We assume that the noise is additive, but since these are enhancement techniques, no modeling of the noise is taking place, other than the basic knowledge that the noise might be broadband and the salt and pepper type of noise, which are special cases of impulsive noise. In some applications, the noise depends on the image intensity, as is the case, for example, in nuclear medical imaging, but this is not something that we'll consider here right now. We will be revisiting noise filtering when we also talk about recovery. So we'll study next both linear space invariant as well as non-linear spatial smoothing filters. Let us look first at the use of linear and spatially invariant systems for performing noise smoothing. The underlying model is that the original image X is corrupted by additive noise W to give rise to the observed data Y. This model, however, is not explicitly used in choosing the filters that we will be talking about. So we want to use an LSI system to filter noise. The system will accept Y, the noisy image, as input, and will provide an estimate of the original image X hat at its output. So H, N1, N2 is the impulse response of the system, and based on what we have learned, the output is simply the convolution of the input with the impulse response of the system. We also know by now that these operations can be taken to the discrete frequency domain. In other words, HK1, K2 is the DFT of the impulse response of the system. Similarly, this is the DFT of the input, and the DFT of the output here can be formed by multiplying the corresponding DFTs as shown here. So convolution becomes multiplication. We also know, of course, that if I multiply DFTs, they have to be of the same size. What happens in the spatial domain is not the linear convolution here, but the circular convolution between the input and the impulse response of the system. We also have learned that if we take the appropriate size DFTs of all the quantities involved here, the result of the linear and circular convolution will be the same. So, in summary and conclusion, we have all the knowledge to perform these filtering operations either in the spatial domain or in the discrete frequency domain correctly. choosing the appropriate size DFTs. Now, if we derive the form of the impulse response here, HN1 and 2, based on the optimization of an objective criterion, then we are solving a restoration problem. If, on the other hand, we try various forms of HN1 and 2 based on our intuition and decide which of those provides us with the best results, then clearly you are solving an enhancement problem. At this point, we're approaching the noise smoothing problem as an enhancement problem. So, therefore, we'll be looking at various filters, at various types of HN1 and 2 that can provide us with meaningful answers. Let us first explain with some simple drawings what takes place in the frequency domain when we are performing noise smoothing with a linear and spatially invariant system. Let us assume here that the signal of interest has a spectrum that looks like this. So I just show one period of the spectrum. I show it as continuous here of the signal. I show it in 1D, it's easier to draw. Then noise is added to this signal, and the spectral density of the noise looks like this. So it's flat from minus pi to pi, and this is referred to as white noise. All frequencies are equally represented in such a signal. So the noise is added to the signal, and therefore the resulting observed noisy signal image has a shape like this. We take the spectrum and it's kind of put on a pedestal. So clearly the objective is to work on this spectrum here and recover as much as possible from the original spectrum of the image, of the signal. However, clearly the noise has been embedded now in the signal, so therefore we cannot just pull out the noise only. So what we do with these noise smoothing filters is to utilize some shape, some low-pass filter in nature that will again allow us to go from here to here, or as close as possible. So as you'll see, depending on what filter we use, the magnitude of the frequency response of the filter, a low-pass filter, looks like this. It might have some simple lobes there, so this is minus pi pi, and the DC is typically 1, no gain or loss. So when I filter, I multiply this spectrum here with this frequency response of the system. So if I multiply the two, then at low frequencies I will preserve the shape of the signal as much as possible. At high frequencies I will bring the signal closer to 0 to just look as close as possible to the original one, but by and large there's a trade-off. I just remove some noise, but at the same time I smooth the signal out. So it will be hard to draw freehand here how exactly the spectrum is going to look like, but it's, let's say, going to look something like this. So this is the spectrum of the estimated signal, which is the result of the multiplication here of the spectrum of the observed signal with the frequency response of the signal. So let's see now in reality how these spectra look like when I use a specific image and examples of these low-pass filters here to smooth out the noise. And again, since this is an enhancement problem, I do not derive the shape of the low-pass filter here based on any specific modeling and optimization, but I just use trial and error. I try this filter, I look at the result. If I don't like it, I try a different filter, look at the result, and again, by trial and error, I try to converge as to what the best possible enhancement is for my purposes. Let us look now at a noise filtering example with a real image. The cameraman image is shown here. It's a 256 by 256 8-bit per pixel image. The spectrum of the signal is shown here. So this is the discrete Fourier transform of the image. We show the 10 log 10 of the magnitude of the spectrum on the vertical axis, while the other axis show the continuous frequency here from minus pi to pi, so we show the basic period of the DFT. We also show a slice through this Fourier transform, a slice going through here at omega 2 equals 0. And the main characteristic, as already mentioned, is that this is a decaying spectrum. The maximum value is found here at 0, and we see that here at high frequencies there are almost 4 orders of magnitude difference. Let's look now at the similar situation with a noisy image. So noise has been added to the cameraman image as shown here, and the corresponding quantities are shown here. So if I go back and forth between these two slides, you'll see that indeed the spectrum is kind of lifted. It's sitting on the pedestal created by this white noise. So the objective is to operate on this noisy image and obtain an estimate of the original one. But again, we don't pose here any optimality criteria. We just are going to try different low-pass in nature filters and see what are the results we are obtaining. For the purpose of this example, we're going to look at flat filters. They're called so because all the values in the impulse response of the filter are equal. So here we see a 3x3 such filter. So that's the support, 3x3, and then again each value is the same, is equal to 1/9, so actually there is no gain or loss when this filter is used. We can look how this filter looks in the frequency domain, so we can take the Fourier transform of HN1 and 2, and we've done quite a few examples like that at an earlier point. So the frequency response is 1/9 due to this term in the middle, plus these two terms. The first term here comes from the combination of these two samples. The one will give rise to e to the minus j omega 1, the other e to the plus e to the j omega 1. I combine them, I can get a cosine. Then the second term is due to these two samples, and then there are two more terms that result from the combination, like this one if I consider these diagonal samples, this and this, and so on. Again, this is something that at this point you should be able to derive with not too much effort, because we studied this again at an earlier point. Actually, it's no surprise that the frequency response h omega 1 omega 2, or the Fourier transform that is of hn1 and 2, is real because hn1 and 2 is symmetric. We also see that h00 here is equal to 1, since all the cosines of 0 are equal to 1, and then I add up all these terms, 2/9 plus 2/9 plus 2/9 plus 2/9 plus 1/9 will give me equal to 1. So let's see how this and other flat filters with different regions of support look like, and what are the results we'll be obtaining by utilizing them in smoothing out the noise in the image we started with. We show here the magnitude of the frequency response of 3 flat filters, a 3x3, 5x5, and 7x7 filter. And at the bottom we show the slice of these transforms through the omega 2 = 0 position. At 0 they're all equal to 1, the log is equal to 0, and then we also see that as the support increases, the width of the main lobe decreases, so it becomes more and more low pass, qualitatively speaking, as the support of the filter increases. We show here the filtered image by the 3x3 flat filter. The noise has been reduced, but also the image has undergone some blurring. This is the spectrum of the image, and this is the slice of the spectrum at omega 2 = 0. So the DC value has not changed. However, the higher frequencies have been reduced here, but also there has been some change in the spectrum at lower frequencies. To better understand exactly what's happening, let's look at the frequency domain. So we have here the spectrum of the noisy image and the corresponding slice, the frequency response of the filter and the corresponding slice, the same location. In the frequency domain, I multiply these two spectra, and what I obtain is the spectrum of the filtered image. Again, this is equal to 1, its log is equal to 0, so this value has not changed. But if you look at the higher frequencies of the noisy image, they have been reduced due to the operation of the filter, and the mid frequencies here have been altered due to the shape of the filter. So this is the frequency domain operation of the filter. However, this does not imply that the implementation of the filter should be done or is done in the frequency domain. As a matter of fact, since this is a 3x3 filter here, a relatively modest support, it makes more sense if I implement this filter through convolution in the spatial domain. This is the result of the filtering by the 5x5 flat filter. The noise has been further reduced, but the image is also altered, is blurred. The corresponding spectrum, the corresponding slice, now the energy or the values at high frequencies are further reduced. This is the result of the 7x7 filter. The image now looks rather blurry. Its spectrum is here, the slice is here. At the very low frequencies, the signal is preserved, but certainly has been altered at mid frequencies and has been altered considerably at higher frequencies. We show here all the filtered images on the same slide for easier comparison. So this is the original image, the noisy image, and the 3 filtered version, the 3x3, 5x5, and 7x7 flat filter. So it should be clear that as the support of the filter increases, it becomes more low pass, qualitatively speaking, which means that the noise is reduced as we move again along this axis here, but also the image becomes more blurry. So if one were to choose from this experiment the image to use, the image that provides a better result, then maybe the one in the middle here would be a good choice, but maybe this one would be fine as well, because indeed the image looks the sharpest here, of course, but not this one, since the image is rather blurry. So this again summarizes this enhancement noise smoothing approach. The noise is broadband. I do not have any particular description about its characteristics, about its probability density function, other than it is broadband, and therefore a low pass in nature filter is going to reject the noise, especially at high frequencies where it dominates over the signal. And then the steps are to try various filters and simply choose the image that is more suitable more useful either when somebody looks at it or provides this as input to another processing step, such as classification, recognition, and so on. We saw in the previous examples that while reducing noise, a desirable effect, we were at the same time blurring the image, an undesirable effect. A way to address this is by introducing special adaptivity to the filter. So now the filter is not processing each and every pixel the same way, but it adapts to the local behavior of the image. So it changes and does a different processing, let's say, at the edges than in the flat regions of the image. So an example of a specially adaptive filter is shown here. X is the input, the noisy image, and Y is the output, the noise-reduced image. X bar here denotes the mean value or the average value or the result of applying the flat filter. All these are synonyms, they express exactly the same thing. Sigma squared of n is the noise variance, while sigma squared of XL is the local image variance. How is this evaluated? We can find the local variance by processing the image. So for an N1, N2 in a neighborhood, we perform this, where the mean, again, we know the expression, but I'll write it again here, is over 1 over the number of pixels in the neighborhood, or the cardinality of n, so again, this is the flat filter or the mean filter, and the examples we had, like if I have a 3x3 region, then this cardinality over the number of pixels here is 9. So we saw the example for, right, we saw the 3x3 flat filter, so it's 1 over 9, the sum of the pixels in it. I can compute the local image variance, sigma of XL squared, and I assume that I know the noise variance, and of course there are ways to evaluate that as well. You can go to the flat region, and the mean is due to the image, and then you can find the variance of the noise that way, for example. So let's see what this filter is doing by looking at two situations. If I'm at an edge, if I'm in an edge neighborhood, then clearly the local signal variance is much larger than the noise variance, which means that this ratio is very small, goes to 0, and in that case we see that the filtered image, it's simply the input image, so we did nothing to a pixel that belongs to an edge, because we don't want to smooth out over edges, we don't want to smooth the image. And actually this agrees with properties of the human visual system, according to which noise is masked by high frequency elements of the image. Edges represent high spatial frequencies, and therefore noise is not visible at the edges while it's visible in the flat regions. Now if I'm in a flat area of an image, of the image, then the reverse is true, that the signal variance, the image variance, is smaller than the noise variance. In that case, I have to constrain that this ratio is not greater than 1, so I have to just constrain it to be, so I'll put this equal to 1, and in that case the output of the image is just the local mean. So this specially adaptive filter, it goes from the two extreme cases. At the edges is the identity filter. It does nothing to those pixels that belong to the edges, while at the flat regions it performs averaging, local averaging. And of course, in between, it's a combination of a min filter and the identity filter with the gain here in the front. So conceptually, what this filter does again, it removes noise in the flat regions, while it lets high frequency information, it lets the edge pixels go unchanged from the input to the output of this filter. So let's see how a filter like this performs on a real image. Here's a noisy image you would like to enhance by smoothing the noise. We see that the noise is visible, especially in the flat regions, such as the clouds here or the sky. If I apply a 3x3 flat filter, this is the result we obtain. The noise has been reduced if we look again at the same flat regions here. However, at the same time, if we look at an area like this or at the antenna here of this building, it's clear that the image is blurred or the resolution has been decreased. If we now apply the specially adaptive filter, this is the result we obtain. The min filter in this special adaptive filter was still a 3x3 filter. We found the variance of the noise in implementing the special adaptive filter by finding the variance of a flat region in the noisy image, like this area, for example. Since the signal is flat, the noise is additive. The variance I measure is the variance due to noise. So here we have managed to accomplish both objectives. One, to reduce the noise. If we look again at the flat regions, it's reduced with respect to the noisy image. But at the same time, we have managed to preserve the sharpness of the image. By looking again at this region or these regions, it's clear that the image, this image, is not blurred anymore like this processed image, and it reflects very closely the original image I started with. The special adaptive filter can be implemented in a straightforward way. It does not increase the computation considerably. Certainly I have to evaluate the local variance. This is the extra computation I perform. However, by looking at this result, it's definitely worthwhile, since the result of the adaptive processing is considerably improved, considerably better than the result of the non-adaptive processing.